A factory consumes 280 amperes with a power factor of 0.65 operating on a three-phase 400 volts and a frequency of 50 Hz. It's necessary to improve the power factor to 0.95. What is the capacity of the capacitors necessary to compensate? What is the percentage of reduced load at the new power factor? This is a practical example which need the power of capacitor needed for improving the power factor at this factory. Firstly, we have to write the necessary equation for this calculation. The real power or the active power equals to this value multiplied by the voltage multiplied by current multiplied by cosine theta. Cosine theta always called power factor. We add these values at the formula and get the answer or the value. So the voltage of the installation or the factory is 400 and the ampere which are consumed is 280 and the existence power factor or the present power factor for this factory is 0.65. So we add these values at this equation and we get the active power of the factory or the real power. So the real power is 126 kilowatt consumed. From the table we find that the ratio between kVAr divided by kilowatt when improving the power factor from this value to this value and will be 0.84. So how we can go to the table and how we can choose this value? Let's go. This table is for easy calculation for improving power factor. This is the present power factor for the factory, 65, and this is the power factor which will be improved too. So the cross between them is 0.84 and this value called the correction factor. The correction factor of kVAr divided to kilowatt. This is the correction factor measured by kVAr divided by kilowatt. And this correction factor is chosen from the table when determining the primary and the final power factor and then multiplied by the value of the load power kilowatt to find the ineffective power needed to compensate kVAr. So after we choose this value, now let's go on doing calculation. This value, which is this value chosen from the table, we can get the reactive power compensated for the factory. So Q or the reactive power compensated equal to this value is equal to this value multiplied by the true power of the factory, and then we will need 106 kVAr from capacitors, and this value is required to improve the power factor from 65 to 95%. Now let's get the value of the apparent power. The value of the apparent power from this calculation or from this value, from this equation is very important. S indicates apparent power and equals to true power divided by the power factor. And this is and this formula we can get easily from the power triangle. So 126 divided by 95% equal to 132 kVA. So the apparent power for the factory is 132 kilovolt ampere. Now let's get the real ampere at the present. Now let's calculate the ampere for the factory at the present power factor. Ampere is equal to 280 ampere. But if we calculate again the ampere at the improved power factor, this ampere will be 191 ampere. So we know that the ampere goes down from 280 to 191. So this is very important to know, and this is a very note to know. When we improve the power factor, so we can get less ampere for the factory. And how about the difference ampere between both values? The difference ampere between these both values called technical losses, and this is ampere, not true ampere, but it's imaginary ampere or inductive ampere, which causes heat for lines, for cables, and for the electrical networks inside the factory. If we calculate the percentage of the ampere losses or ampere reduction, we can get 31.7%. This is the reduction of ampere when we improve the power factor from 65% to 95% ratio of loss reduction. So you have to calculate very well the ampere at the present value and the ampere at the final value of the power factor. So you have to calculate the percentage of the reduction. We find that the insulation of capacitors with a power of 106 kVAr makes the current needed to operate the factory decrease by 31.7%, and the power factor improves to 95%.